Everyone, my name is Anjali. I am one of the TAs for the IBC 102. The purpose of this video is to help memorize the 10 different steps in glycolysis, specifically focusing on the 11 intermediates, and I'll be putting each intermediate of glycolysis in a location on campus and providing a path from the very first intermediate, glucose, to the very last intermediate, pyruvate. And the UCSD campus will sort of be like analogous to a cell in your body. Yeah, and we will also be going over different parts of the process in detail as well throughout the map to keep us oriented. So with that being said, let's get started. So here's the general map that we will be using, and you'll become familiar with it soon. We'll be placing the first intermediate of glycolysis, glucose, in the bus. Hey everyone, so I'm on the bus right now heading to campus, and I'm going to be placing the first molecule we have in glycolysis, which is glucose, in this bus. That's because public transport to me is a lot like the circulatory system of the body, allowing us to get from one part of the city to another. Similar to how we can travel throughout the city in public transport, glucose can also travel throughout the body in the blood. So the first intermediate of glycolysis is our glucose molecule, which is a 6-carbon sugar. And the 6-carbon sugar is able to move freely in and out of cells, and it's able to travel freely in the blood. So we need to figure out a way in which we can trap this glucose molecule within a cell, because glycolysis takes place within a cell. How do we do that? We do that by phosphorylating the glucose with a phosphate group from ATP, and this is done by the enzyme hexokinase. So ATP is losing a phosphate group and it's becoming ADP, and glucose is gaining a phosphate group and it's becoming G6P. And this effectively traps the glucose molecule within the cell. This step is also irreversible, so that is something you should note down. That brings us to the second molecule in glycolysis, which is glucose 6-phosphate, and we'll be placing that molecule in the Gilman Transit Center. Great, so we're on campus and we're at the Gilman Transit Center. So in my analogy, the cell is analogous to the UCSD campus. So we're finally entered the campus, and oh no, look what happened. I just got flyered. I have a GBM tonight apparently, and that means that I am trapped on campus till tonight. Similar to how glucose 6-phosphate is trapped in the cell once it is phosphorylated. So we are here now, which is our third molecule, fructose 6-phosphate, which is an isomer of glucose 6-phosphate. The enzyme that turns glucose 6-phosphate into fructose 6-phosphate is very namely, it's phosphohexose isomerase, because we're making an isomer. And what an isomer basically is, it's a rearrangement of the same chemical formula, the same atoms, in a different manner. So if you take a look at glucose 6-phosphate and fructose 6-phosphate, you will see that the same formula is being used for both, but they're just arranged differently. And this step is reversible. Whenever you see these arrows, that means that the step is reversible, unlike the previous step, which was irreversible. We will be placing the third molecule, fructose 6-phosphate, on library walk. And we are at library walk now. Look how empty it is because it's a Sunday, no one is on campus. And look what I am doing over here on library walk. I am taking the glasses off my shirt and putting them onto my face. I'm rearranging my quote-unquote outfit, similar to how glucose 6-phosphate is rearranged into fructose 6-phosphate. I'm becoming an isomer of myself. Whoa, is that a basket of fruits on library walk? That reminds me of fructose 6-phosphate. Haha. So our next molecule will be fructose 1,6-bisphosphate, and this molecule is kinda unstable because we now have another phosphate group added onto fructose 6-phosphate. And that phosphate group comes from ATP, and it's added by the enzyme phosphofructokinase 1. And we know that kinases, that's what they do, kinases phosphorylate intermediates, right? This is a highly regulated step, and it is also irreversible. This fourth molecule, fructose 1,6-bisphosphate, will be placed on fallen star. Alrighty, so I am here in the engineering part of campus, which I honestly do not really ever set foot on, but here is fallen star, and it's supposed to represent a fructose 1,6-bisphosphate, because look how unstable it is. It looks like it's going to fall apart any moment, and fructose 1,6-bisphosphate is also similarly unstable. So in the next step, we break apart fructose 1,6-bisphosphate with the enzyme aldolase, and that gives us two intermediates, G3P, which is glyceraldehyde 3-phosphate, and DHAP, which is dihydroxyacetone phosphate. Of these two intermediates, the one that we are most interested in is G3P, because that is the molecule that moves forward in glycolysis. DHAP is mostly converted to G3P in order to move forward in glycolysis. And how does that happen? DHAP is converted to G3P in this reversible step here. Triose phosphate isomerase converts DHAP to G3P because they're isomers of each other, so it just rearranges the molecules. Whoa, it looks like fallen star just fell, so that represents fructose 1,6-bisphosphate breaking apart into two. So one part of fallen star, DHAP, has fallen into the valley, represented by number 5 here, and it's in the valley because it is no longer moving forward in glycolysis as DHAP. It is moving forward in glycolysis only after being converted to G3P. Number 6 here, which is the other part, and that has fallen into Geisel, specifically the third floor, because I want you to remember that is G3P, and obviously the third floor is the best floor of Geisel. And with this reversible step, we are seeing the end of our energy investment phase of glycolysis. So as we move away from this phase, I just wanted to give a little recap of what we've seen so far. So first we saw glucose just floating around in the bloodstream, and we designated that to the bus. And then we phosphorylated the glucose with the phosphate group from ATP to make it G6P in the Gilman Transit Center. And then G6P was made into an isomer fructose 6-phosphate, and that was on library walk. I put on my glasses and we saw some fruit to make it fructose 6-phosphate. And then we went to Warren, to the fallen star, where fructose 6-phosphate was phosphorylated with a phosphate from ATP, and we designated that location to fructose 1,6-bisphosphate, which is very unstable, and it breaks apart into two molecules, DHAP and G3P, and DHAP is also being converted to G3P because only G3P is able to move forward in glycolysis. We will be moving towards the energy expenditure phase of glycolysis. So the first part of the energy expenditure phase of glycolysis has a redox reaction where G3P is converted into 1,3-bisphosphoglycerate. And this is a redox reaction because NAD here is being reduced to NADH, and G3P is being oxidized to 1,3-bisphosphoglycerate. And this is conducted by the enzyme glyceraldehyde 3-phosphate dehydrogenase. G3P is also being phosphorylated in this step as well, with the addition of phosphate groups. And if you notice here, you'll see that there are two of everything, because you have to keep in mind that DHAP is being converted to G3P and is also moving on with all of this side by side. So that's also occurring. That's why we see two of everything. And this is the one and only redox reaction that you will see in glycolysis. We will be placing 1,3-bisphosphoglycerate, which is the 7th intermediate of glycolysis, in the sun god lawn. On my way to the sun god lawn. Here we are, and oh my god, what do I see? To my surprise, the sun god has been replaced with a red ox. A red ox. A red ox. A red ox. Redox? Redox? It's almost as if I wanted to remind you that the conversion of G3P to 1,3-bisphosphoglycerate is a redox reaction. Alrighty, so now we find ourselves at the 8th intermediate of glycolysis, which is 3-phosphoglycerate. And in order to get from 1,3-bisphosphoglycerate to 3-phosphoglycerate, we are losing a phosphate group and we are producing ATP. So, wow, yay, our first ATP production here, and it is done by phosphoglycerate kinase. And we remember that kinases are responsible for adding phosphate groups. So here, kinase is removing the phosphate group from 1,3-bisphosphoglycerate and adding it to ADP to make ATP. Alright, so now we have 3-phosphoglycerate. And we will be placing 3-phosphoglycerate in Art of Espresso, one of the best coffee shops on campus. Righty, so we have made it to Art of Espresso, and we're at a coffee shop for this step because just like ATP is sort of like energy, coffee also symbolizes energy, because after I drink my coffee, I suddenly have all this energy. And I've gotten a double shot of espresso here because for every cycle of glycolysis, we're making 2 ATP in this specific step. Now we are here at the 9th intermediate of glycolysis, which is 2-phosphoglycerate. We're going from 3-phosphoglycerate to 2-phosphoglycerate by changing the position of the phosphate group, and this is done by the enzyme phosphoglycerate mutase. 2-phosphoglycerate will be placed on the hump in the old student center, and you will see why in just a second. So now we're at the hump, and it's a surprisingly windy day today, as you can see from my hair just flying around me. I had to move my hat from my head to my hand because the wind was about to blow it away, and this is very, very similar to how phosphoglycerate mutase moves the phosphate group from one part of the molecule to another part to make 2-phosphoglycerate from 3-phosphoglycerate. Alrighty, so that brings us to phosphoenolpyruvate, our 10th intermediate. A lot of people call phosphoenolpyruvate PEP because it's easier to say and write. So we convert 2-phosphoglycerate to phosphoenolpyruvate, or PEP, with the enzyme enolase, and this also releases 2 waters. So something that is cool about phosphoenolpyruvate is that it is a very, very high energy intermediate in glycolysis. This is very important. It's a super cranked up molecule, which is why we will be placing this molecule of PEP in the gym, because I like to go to the gym when I have a lot of energy. And I also sweat a lot in the gym, so that could help you remember that water is also being produced in this step as well. Alas, we have made it to the final intermediate of glycolysis, which is pyruvate. We are going from phosphoenol pyruvate to pyruvate with the help of our enzyme pyruvate kinase, and in doing so we are dephosphorylating PEP and making ATP by transferring this phosphate to ADP. One thing that is super important though is that this is an irreversible step. This is irreversible. Does not go both ways. And it is highly regulated step. So because ATP is made in this step, we will be placing pyruvate in another coffee shop on campus, Mom's, middle of Muir. This is me on my way to Mom's. And lo and behold, I am ordering a coffee with 2 shots of espresso. Again, because we're making 2 ATP in this step. Again. Shout out to our wonderful barista here, Molly, who agreed to be filmed for this video. Coffee has been ordered and now I am pyru-waiting for it. See what I did there? And here I have my coffee and we are ready to go. And with that is the entirety of glycolysis. Congrats, my friend, you have walked through the campus of UCSD and walked through glycolysis at the same time. So, what are some important things that you should remember? So here, we have made a total of 4 ATP. However, we used 2 ATP, so that gives us a net of 2 ATP produced throughout glycolysis. And we have also made 2 NADH from 2 NAD, and we have also made 2 H2O. So the net reaction yielded these molecules as well as 2 pyruvate. Another thing to remember is which steps are highly regulated and which steps are irreversible. So these steps are irreversible over here, and the highly regulated steps are PFK1, the conversion of F6P to fructose 1,6 bisphosphate, as well as the conversion of PEP to pyruvate. So this is the highly regulated step 1, and this is highly regulated step 2.